Now we continue with the next lecture that is a bit more on mathematical morphology. So we saw in the last lecture the median filter, and the median filter was categorized as part of these mathematical morphology operations. And we will see now more mathematical morphology operations, but now on binary images. So yeah, let's go to the next one. So yeah, it has very nice mathematics behind, and they are based on this Minkowski set theory, and yeah, it has a lot of connections to the theory of finite lattices and many other things. But the main idea you may keep is that they are non-linear operations. So all the operations we will see now, they are non-linear. We saw it already with the median filter. The median filter is also a non-linear operator. And it can be used to many applications. And here you have a few of them. So, image enhancement, image segmentation, restoration, edge detection, many different things. Okay, so let's see what it is about. So they are, or these operators we will see today, they are for binary images. And binary images is an image that takes two values, that is binary. And what are these two values? We don't care. So they can be 0 and infinite, 0 and 1, 0 and 255. You may revert them if you want. So you can say instead of 0 and 1, 1 and 0. So they can be whatever. The important thing is that we have two values, one for the foreground, another one for the background. And I think during the lecture we will assume these two values, so 255, 0. So 255 for the foreground, 0 for the background. And okay, so what is the foreground and the background? So the foreground is the set of pixels where the intensity value at that location, at the location P, takes the value of the foreground. Okay, so it is the set of pixels such that in this lecture, the intensity is 255. And the background are those pixels whose value are 0. And so these are sets. Okay, so those are sets of pixels. And then you can do the standard operations with sets. So you can say, for instance, the union of the foreground set and the background set has to be the image. The image considered as a set. And the intersection of these two sets has to be an empty set. And then the background is the complementary of the foreground set, and the opposite. The foreground is also the complementary of the background. So here you have an example. So let's say that we have this binary image. It is 255 here, it is 0 here. And then the background is the set of all pixels that are black, and the foreground, the set of all pixels that are white. So those are sets. That is the important message so far. And we may define another set that is the support. So the support is the set of locations. It is not the set of pixels. It is the set of locations where the intensity takes the foreground value. Okay, so it is the set of locations that have a value 255 here. Okay, so we may define, instead of the support of an image, we may define the complementary of the support of the image. That are all those locations where the intensity takes the background value. Okay, so we have this image. So this is the support of the image. So let's say that we binarize this image so that where we have the shapes, we have value 255, and in the background we have a 0 value. Then this would be the support of the image. And the complement, that is the outside this region, we have the support of the complement of the support. Okay. And we will need another element for defining mathematical morphology operators. That is this structuring element. So the structuring element, it is a kind of kernel, but now it is binary kernel. So here, just for representation purposes, the background is white and the foreground is black. So this kernel that is called set 8. So set 8 is a pixel and the 8 neighbors. And these 8 neighbors, we can compare set 8 with set 4. So in set 4, all the copy, I think it is more clear if we draw it. Okay, so copy. This is okay, one. So let's copy this one. Let's go to the whiteboard. Okay, so here in set 8, we have this pixel and we have this one. And you may see that all the boundary is an edge of a pixel. Okay, and it is the same with the other 4 neighbors. And a property of set 8 is that a pixel is a neighbor of the center, so it is the same as here. If they share an edge or they share a corner. So these are the pixels here. They share a corner with the central one. So this connectivity later will play an important role. So what is the connection between the neighboring pixels and the central pixel? Okay. And you may think of this as a kernel. So it is the connectivity is whether you are sharing an edge or you are sharing an edge or a corner. Okay, good. So yeah, so we can define these 2 kernels, so you can define any other kind of kernel that you like. So you may define this one, they don't have to be centered, so or symmetric around the center. Even the central pixel may not need to be active. So for instance here, you have the only active pixel here is away from the origin. So the origin is marked with a circle. So here the active pixel is displaced with respect to the origin. So this is a kind of equivalent to the shift operator. So in a shift operator, you have a delta that is not at the origin. It is shifted with respect to the origin. So these kernels, in this context, they are called structuring elements. Okay, so we will define this operator, that is the shift operator, so that if you have a structuring element, you may shift it to the location P. Okay, and we will denote that as Z plus P. So P is a location, and Z is the structuring element. So let's say that you have this structuring element, and you have this P. So Z plus P will be the structuring element displaced to that location. And this Z plus P will be called the Z neighborhood of P. Okay? So Z plus P is the Z neighborhood of P. So it is the neighborhood of P according to the structuring element Z. And we will denote that also in this way. So it will be the neighborhood of the location P, and this neighborhood is defined by the structuring element Z, and it is applied to an image I. And we are still defining more operations because we will need them. So the next operation we will define is this reflection. So we will denote a reflection with this arc. So if you have a structuring element Z, then the reflected one is the one whose support is just the negative of the support of Z. Okay, so it is all those locations such that this is wrong. So the first RC is wrong. So it is minus R minus C. So you take the structuring element, you flip it with respect to the origin, you mirror it. So here, for instance, it is very well shown. So, for instance, you have Z2, that is this particular arrangement of pixels, and if you reflect it with respect to the origin, then you have the mirror one with respect to the point. Okay, so ZR is the structuring element that is formed by mirroring a structuring element with respect to the origin. And here you can also see, so you have this Z3, and then you reflect it. Here Z2 and Z3 is simply just to say this is Z1, Z2, Z3. So they don't have special names. These two, they have special names. This Z8 and Z4, they have special names. This is just to say this is the first kernel, second kernel, third kernel. And if the kernel is symmetric, then mirroring it doesn't matter, so it stays the same. So this is this example. And actually, this is already known for you probably. So mirroring with respect to a point is the same as rotating 180 degrees with respect to the origin. Okay, so mirroring in this way, so mirroring both coordinates is like rotating 180 degrees. And you may easily see this if you think of the rotation matrix. So if you think of the rotation matrix with an angle theta is cosine theta sine theta minus sine theta cosine theta. So a mirror of 180 degrees, is cosine of 180 degrees, but that cosine is minus 1. And then sine of 180, so you have this. So if you multiply any coordinate by this matrix, so you multiply this one by xy, you get this minus x minus y. So computing a mirror in both directions, in x and y, is the same as rotating 180 degrees. That doesn't occur for the other mirrors. So this mirroring is this one. So you have a point here at the coordinate, let's say this is x, this is y, this is the coordinate xy. So the mirror point is this, and this is minus x minus y. There are two other ways of mirroring. So this is a mirror with respect to this point. And there are two other ways of mirroring. One is this one. So you are mirroring with respect to this axis. And then this coordinate would be minus xy. And there is another one, that is this one. That is x, that is x minus y. So this one can be achieved with a rotation. This other So you cannot find any notation that give you this kind of mirroring. So, okay, so yeah, we have the mirroring operator. And now we will start to introduce the mathematical morphology operators. And the first one will be dilation. So the dilation will take a binary image and make the foreground bigger. So this is these are the pixels that are active in this binary image, and then after the operation, you will have more pixels. And we will define it, this operator, in 3 different ways. And actually, this is very much the same as what we can do with the convolution. So you can think of the dilation as a convolution, more or less. Okay, so let's see how it is defined. So we have a first definition. This is set. Okay, it is I dilated by set. So I dilated the set by set is the set of all locations that belong to the support of the image I, such that when you reflect the kernel and place it at the location T and compute the intersection with I, it is different from the empty set. Okay, so let's see. Yeah, here we have that. Okay, so for instance, let's say that we have this image here. We have this. This is the reflected extraction element. So we will go for all the pixels in the input image, such that when I place my reflected extraction element there, and I compute the intersection of this reflected element with the foreground pixels, the intersection is different from empty set. Okay. So this one, the intersection is an empty set, so that location will not belong to the dilated. And what about this one? If I place the extraction element here, then the extraction element there, it has an intersection with this foreground pixel. So this location will belong to the dilated. And the same for all other locations. So this location belongs to the dilated, so we will put it active in the output. And then you can compute for all other positions, which are the positions that have an intersection with the foreground image. And then every time you find an intersection, you draw it in gray in this output image. And then these are all the possible locations, and at the end, what we have is this result. And this makes sense, and it goes in the direction of the convolution. If I convolve a kernel with a delta, what I should see is the kernel shifted to the location of the delta, and that is what we are having. So this is my kernel, and if I convolve my kernel with this delta, what I see is the kernel shifted to the location of the delta. And during the calculations, I have needed the reflected kernel. Let's think of this in one dimension and in convolutions. That is something that we are more familiar with. Okay, so let's say that I have a signal. Let's say I have a signal. So this is my x of n. And this is n. Let's put some numbers here. So this is n minus 1. Okay, and I want to convolve this. I want to convolve this with this kernel. This is the typical low pass filter. first order low pass filter. Okay, so let's write the formula. Okay, so the formula is y when that is the convolution of the two is the sum of x of n, h, n minus n minus. Okay, so let's look at this term here. This term there. Yeah, let's separate the two. So let's make different one. This one. So that one means now this is the axis m, and this will be x of m. But it has the same shape as it had originally. Okay, what about the other one? For the other one, what I'm doing is I have the axis m. This is h of n minus n. So I have to invert my kernel. So I have to reflect my kernel. So this is a mirror of my kernel with respect to the origin. So the origin in one dimension is just a point. In two dimensions it is also a point, but I have to mirror both coordinates. Here I'm mirroring just one coordinate. And what is the mirror? The mirror is here. So, the mirror is in this negative sign because I'm in the axis m, and the coordinate m has been mirrored by this negative sign. So I'm doing the same. So when will I have a convolution that is zero? So my convolution will be zero. So yn will be zero if there is no intersection between these two signals. So for instance, if this signal moves too much to the left and there is no intersection, so for instance, it moves to this location, this is n, then this is, always remind to label your axis, right? This is h of n minus n. So if my kernel moves to a location where there is no intersection between this one and this one, then the output will be zero. So it is the same that is happening with the dilation. If there is no intersection between my mirror kernel and my input image, the output will be zero. And the difference between this operation and the other one is that I'm simply saying there is intersection, yes or no. And while in the convolution, I'm summing what is the product of this intersection. So I'm multiplying point by point the two images and then making an addition. But otherwise, they have a very similar flavor. Okay, so yeah, this is one definition, and we see that this somehow is similar to this convolution that we have defined before. And actually, I can find two other expressions for computing my dilation that also they are very much related to the convolution. Okay, so let's look at the first one. The first one is you take the kernel and you displace it to all the pixels in the support of the image. So the support of the image is all those locations that the image is different from zero. And you displace your kernel to that location. Okay, so let's see why. So this is a property of the convolution actually. So if I look at this convolution, let's say that x of n has a lot of zeros. Okay, so x of n has a lot of zeros. So I will express this one. I will express this one as a sum of for all those locations where x is different from 0. So n0 belongs to all the locations where x of n, so let's make more precise. So those are those locations such that x of n 0 is different from 0. But this is the definition of the support, right? So this is the support of x. It is the defined locations where the signal is different from 0. Okay, so this is x, and now I have to convolve with my kernel. But this is the same as, okay, so this is a scalar, this one is a scalar, and this is a delta. So what I have is my kernel convolved with a lot of deltas. So what I have to do is you move. So for all the points that belong to the support of x, you have x of n0, and then your kernel is placed in that location. So you have a sum of your kernel displaced to the locations of n0 and then multiplied by the input signal at that point. Let's look at the dilation. So for all the points in the support of the input image, we shift the kernel to that location, and instead of adding and multiplying by x of n0, we are simply computing the union. The union and the sum, they are very much related operations. So this is the same as we had before. And what about this one? This one is, instead of the support of the input image, it is the support of the kernel, and then you are shifting your image to the location of the support of the kernel. So instead of expressing x of n as a sum of deltas, I could express h as a sum of deltas. So I take now, this is x of n on board, and I do the same trick as before. So for all the points in the support, but now the support of h, and this will be h of n0, and then the delta there. And this is the same. So this is the same as the support, the sum over the support of h, and x displaced to that location. So it will be h of n0, and then x shifted to that location. So I can either expand at the level of the support of h, or I can make my expansion at the level of the support of x. Clear? Okay, so, and this is the same here. So dilation is very much, you can think of dilation as a kind of convolution, but now with binary images. And then you have to redefine a bit the concept of convolution, because in convolution you are multiplying by a scalar and then adding, and here you are simply computing the union of sets. But it's the same. And here you have some results, for instance, some example. So let's say that we have this input image here, and then you dilate with Z8. Z8 is the one that has 8 neighbors around. And then we have plotting in yellow the location of all the pixels such that if you mirror your kernel, your instruction element, to that point, and you compute the intersection with the input image, that intersection is different from the empty set. Okay, so if I move my instruction element to this location in the middle, for instance, my intersection with the input image is different from 0. And the same happens for all these pixels here. This hole, if I move my instruction element to there, and I compute the intersection is different from the empty set. And the same here, the same here. So this dilation is a way of filling holes. So if I have a binary image with holes, and this is a hole, this is a hole, this is a channel, so I can fill the holes. And yeah, we have already seen this one. Yeah, this is how to make a fast calculation of the dilation. So a fast calculation of the dilation. Normally, this expression here, the support of the kernel is relatively small, so it is much simpler to shift your image to the location of the support of the kernel, and then you make the union of all those images. And here you have that example. So, for instance, let's say that we have this input image. This one is the central pixel of the kernel, and it is the same as, I think it is fine now. I think it is this one. Okay, so this would be, I have to shift my input image, that is this one. I have to shift my input image to the location of my kernel, of the support of the kernel. So I shift my input image to this location, that is this one, to this other location, that is this one, and so on. And then you add all of those. Add in the sense of union. And here you have more examples. So let's say that you have this original image, and then you have this structuring element, and now you shift your original image to the location of the deltas of the kernel. So I have to shift it to here, so I shift it up and left, and I have to shift it to here, so it is shift to the left, down, and then you compute the union of all these images. The union of all those images is this one. And what is in red here is the shape of the original image. Okay, so we have dilation already. So we can now define a new operator that will be erosion. So erosion is defined in this way. So the symbol is this one. I didn't mention that, but the symbol of dilation is this one, this glass with a circle. So erosion will be minus with a circle. So erosion takes a foreground, so takes the foreground of an image and makes it smaller. Okay, so this is the original image, and this is the eroded version. Okay, so how to do that? So it will be the set of all locations in the support of an image, such that when I shift my kernel to that location, it is totally included in I. It is totally included in the image. Let's see some example of that. We don't have a nice picture like that. Yeah, so let's say. So let's say that my structuring element is Z8. So this is the original image. So which is the location? Which are the locations that if I shift my structuring element to that location, it is totally included in the image. So for instance, this red pixel here, if I move my structuring element to that location, it is totally inside the original image. So that is kept. So that is red will be our output. And the same here. So if I shift my structuring element to that location, then it is totally included in the input image. What about this pixel here? So this pixel, if I shift my kernel to this location, to that particular location, part of the structuring element is outside the image. So it will not be kept at the output. Okay? So this single pixel disappears. So you can think of this now as, instead of filling holes, as we had before with the dilations, it is filling holes in the background. So this pixel, if you look at it from the point of view of the background, it is a hole. It is just an isolated pixel of the foreground. So it is like filling holes, but now filling holes in the background. And the same happens here. So this is a small channel, this is a small channel in the background, so I'm filling the background. And in the same way as we had before, I can redefine, not redefine, I can express this definition in two other ways. So this is the first way. So it is you go for all the pixels in the support of the image, and you compute the intersection of all your reflected kernels moved to that location. So you have a lot of these kernels that are located at the locations of the support of the image, and then you compute the intersection of all those sets. And instead of the support of the image, you can find the equivalent definition now in terms of the support of the kernel. Not the kernel, but the reflected kernel. So you take the reflected kernel, and you move now the image to the location of the reflected kernel. So those are kind of equivalents to the definitions we have here. So here we had an expansion in terms of the locations of the support of the image, and here in terms of the locations of the support of the kernel. So now we have the same, but now instead of unions, we have intersections. Okay, so yeah, and the one that has the expansion in terms of the support of the kernels, because the kernel is typically small, will be faster. Okay, so here we have a comparison of the two operators. So we have in gray we have the original image, and then you have in red the erosion, and in yellow you have the dilation. And we have used here as kernel, as a structural element, we have used the Z8. Okay, so now we are dealing with sets. So there are extensions of something, of some properties that you know already for sets. So for instance, have this one. So for a set, you know that you have two sets, A and B, and you want to compute the complement of these. You know that the complement of this is this one, right? Now the name of this guy, what's the name of this guy? No. Morgan. Yeah. So, and you have another one that is, those are Morgans. So you know this for seconds. So now let's look at what we have here with the. So for instance, we have I minus C. So we have I eroded by C, and then complement. So the complement, let me write it in this way. So so if we follow the analogy with the Morgan laws, this would be the complement of I, and then I have to change the operator. So here we have intersections. The complement of an intersection is a union. So the complement of an erosion is a dilation. And then instead of the complement, it will be the middle one. But this is what we have. Okay. You see. And you can compute, we have a kind of equivalent Morgan's law, but now for the dilation. So it will be I, and I have to change my. You see? So because we are dealing with sets, we are starting to see kind of Morgan's laws that are the ones that are applicable to sets. We start to see them, but now in terms of dilations and erosions. And we have more properties. Here you have a few more properties. So this is just, if you complement on both sides, so you compute the complement of the left hand and the right hand side, then the complement of the complement stays the same. So you have now other ways of computing the erosion, for instance. So we have given these three expressions for the erosion, but here you have another one that is based on the properties of the erosion. So the erosion can also be computed as the complement of the image dilated by the reflected element. And we can complicate this a bit more. So we can define new operators. So once you have very basic operators, you can start to compound them. So for instance, you can compute the opening and the closing. So the opening is first you erode and then you dilate. And the closing is the opposite. First you dilate with the mirror and then you erode with the mirror. And these are called the opening and closing operators. And here you have an example of the opening. So first you erode and then you dilate. So this will be the result. We will see how we get that. So the erosion, so we start with the original. This white one is the original. Then first you erode, so you delete part of the input, and then you dilate whatever survives. So these red pixels have survived, and then you dilate them. And here is the superposition of the two. So an opening is a way of getting rid of so erosion is filling the holes in the background, so or getting rid of thin objects in the input image. So we first get rid of the thin parts, so these isolated pixels, and then the thick parts, they survive the erosion, and now we dilate them to try to recover the original. Okay, so we don't fully recover. All the thin areas, they have been deleted. And yeah, this is the opening solution. Yeah, it is the same, but now in 2 steps. So from the original, you complete the erosion, and then from the erosion, you dilate. And there is a property that is that the open image, so the opening of an image is always included in the image. So all the pixels in the opening, they were originally in the image. And here is another way of reading that. That is, an opening can be computed as the union of translated copies of the kernel subject to the constraint that the opening is contained in the original image. But okay, we understand what the opening is. And as you can see here, the closing, the effect is filling the holes of a foreground image. So you have here a hole, and then it will be filled. Okay, so here you have the original image, and then the dilated version in yellow. And then, so the dilation will be filling the holes, and then we erode the filled one, so the dilated one. So this hole now, this hole that was isolated in the input image, now it is filled, and then the erosion cannot start from there. It cannot be a seed for the erosion. All the pixels in the boundaries, they can be used as seed for the erosion, and then you get the dilated pixel, you get it back to the original, and this is the original. Now this is the result, the closed. Okay, so here we have the whole process again. So we have the original, the dilated version, and then the erosion. And these two properties we already saw. So these are kind of Morgan laws for the dilation and erosion, but we have also Morgan laws for the opening and closing. So these are the equivalent of the Morgan laws for the erosion and for the opening and closing. And here is an example with asymmetric structuring elements that are less common, but in some applications they are useful. And they're certainly useful to understand what is happening. So here we have the original, and we are convolving now with this L that is off-center. So original dilated by this is this one, and the erosion with this structuring element. So you can think of this as filling the holes with a particular shape. So with the set A, we are filling the holes. Buenas noches, Ana.
Soldado López y dice, sí, mi capitán, ayer no leí las pruebas de camuflaje. Muchas gracias, señor.
Hoy nos fuimos por la calle y hace mucho calor, entonces dice uno, ojalá lloviera, y dice otro, ojalá yo también.
Okay, so now you can think of this filling the holes, but filling the holes with a shape. So for instance, here it is very clear. So for instance, here, filling the holes with an L shape. And this is the closing, this is the dilation, and here these borders here, what they are meaning is that, as always with images, when you go to the borders of the images, these operations are ill-defined. And the same happens with the kernels. We have seen it a few times, that we have to take decisions what to do at the boundaries. And we have seen this mirroring at the boundaries, making the image periodic. So at the boundaries, we always have problems. Yeah, this is the same. What happens if, so let's say that I have an image that has a size Ri original, RICI. So Ri rows, Ci columns, and then this CSE is the number of columns of the structuring element. So that will be a region that is defined. You have here the particular expressions, but we don't care so much about the particular calculation of how many pixels. But the idea is that at the boundaries, and the boundaries are defined in something that depends on the size of the input image, the size of the structuring element, and the offset of the structuring element. So what is where the origin of the structuring element is. But okay, we don't care about all these small details. Okay, so let's use these operators now to detect borders of a binary image. So let's say that we have this binary image, and I want to detect the borders of this binary image. So what is a border? A border is a pixel that is in the foreground, but is surrounded, or it is close to the background. So for instance, this pixel here is not in the border because it is completely surrounded by foreground pixels, while this pixel here is in the border because it is surrounded by some background pixels. Okay, so let's see if we can use these operators that we have already to detect borders. So for instance, I can take this binary image, I can erode with a square, so the square is Z8, so this 8 connected structuring element. And I can compute the difference between the original and the erosion. So if you compute the difference, this is what remains. And now, if you look at these pixels in the original image, they were with some background pixel around. Okay, so all these pixels that remain, they have some background pixel around. And here it comes an interesting label. This 4 connected inside boundary. So 4 connected means the boundary is formed by a shape where all the pixels, they have 4 connected neighbors. And this is related to what we were explaining before at the beginning of the lecture. Sorry. The beginning of the lecture about how we are sharing when we define something as a neighbor. So in this set 4, the neighbors were defined by sharing an edge, while in set 8, the neighbors were defined by sharing an edge or a corner. Okay, so if I put the borders in this way, so eroding with set 8 and then computing the difference, the border is defined, the boundary is defined as pixels that they share a 4 connected neighbors. So all the neighbors here, they share an edge, all of them. Now, instead of using set 8 to do the erosion, I use set 4 to do the erosion. And now I compute the difference. Now, my boundary is made by 8 connected boundaries. So now, for instance, these two pixels, they share a corner, they don't share an edge. You can see the difference with this boundary before. So it depends on how you want to compute your boundaries. So do you allow for only for 4 connected boundaries, or you allow for 8 connected boundaries? So 8 connected boundaries, they are weaker in the sense that the connection between pixels, some of the connections are weaker. So this is only just a corner, just a point. While this 4 connected boundary, all the pixels, they share an edge. It is a much stronger connection. And there is another label here, inside boundary. So inside boundary is a boundary that is contained in the original image. So all these pixels here, they were contained originally in the foreground of the binary image. Now, let's say that I take the original, and instead of eroding, I dilate with a Z4. Z4 is this glass kernel. And now I compute the difference between the dilated minus the original. So dilated minus original, now it is an outside boundary. So the boundary is not contained in the image, it is contained in the background. And if I use here this 4 connected structuring element, then the boundary is 8 connected. And the same as before, if the structuring element is 8 connected, then the boundary is 4 connected. So the boundary is connected by edges, or here it is connected by edges or corners. So now we have 4 ways of computing boundaries with these binary operators. So we have 4 connected, so these are strongly connected boundaries from the inside, weakly connected boundaries from the inside, weakly connected boundaries from the outside, and strongly connected boundaries from the outside. And all we have done is dilated minus original, or original minus eroded, and then choosing the kernel. So those are our options. Yeah, so, and there are properties. So that, for instance, this property here, that the 4 connected outside boundary is contained in the 4 connected outside boundary, for sure. So the weakly connected outside boundary is in the strongly connected outside boundary. And the inside boundaries are disjoint with the outside boundaries. So a pixel either belongs to the inside boundary or belongs to the outside boundary, but it cannot belong to both. And so you can analyze all kinds of properties of these boundaries. Okay, so let's refine a bit more these concepts. So now, let's say that I want to dilate, but only within a mask. So let's say that I have this original image, and I want to compute the dilation only within this mask. Okay, so what I can do is, okay, you compute the dilation with everything, and then you mask the part that you want to keep, and then that part you keep it, and then outside the mask you keep the original pixels. Okay, so now this operator that is using a mask, it is very easy use of a mask, but this operator that uses a mask is a dilation only within the mask, and that is called conditional dilation. Dilation conditioned to a mask to be 1. And I can use these condition dilations to identify objects. For instance, let's say that you have in an image, you have two objects like here. So we have you have a square and a diamond, and you take so you want to identify this is object 1, this one is object 1, this one is object 2. Okay, so how do I do that automatically? So I take a pixel from the foreground that is not labeled. So at the beginning, I don't know how many objects I have. So all the pixels in the foreground, they are unlabeled. Okay, so I take the first pixel that is unlabeled. Let's say I take this one, and I assign the label 1. And now I dilate my image. So I dilate my tag, my label, condition to the original object. So condition, this dilation condition to the original object gives me these two other pixels. And now I have a new set, that is this one, and I can keep doing that. So you dilate, and now you condition to the original object. And now you have these two other pixels. And you keep doing that all the time. So dilate, condition, dilate, condition. And at some point, you will detect all the pixels that are connected. And at some point, if you dilate and condition, there is no change in your labels. So you are not discovering new labels anymore. So at that point, the process has converged, and you have identified already one connected component. And here you can already figure out that that is connected, and we can put another label to that. That is 4 connected, 8 connected components, and all that, depending on what is the structuring element that you are using. So if you are using set 8, here you have a connected component that shares corners. If you use set 4, then all these components cannot be connected because they only share corners, they don't share edges. So the connectivity of an image, of an object, depends on what is the structuring element that you are using. This is another application of these operators. So here, let's say that you have this original image where you have a bit of binary noise, and then you want to get rid of the noise. And what you can do is an operator that is called binary reconstruction. So getting rid of these white spots could be done with the opening. So for instance, the opening gets rid of the spots, but they also get rid of fine details in the input image. So for instance, the eyes have disappeared. So this is not nice. Okay, so let's we have to find some other way of combining the operators to recover the eyes. Okay, so let's see. So the following steps, they are called binary reconstruction. Okay, so you start with an image, you compute the opening, and now you start to iterate. Okay, so the first iteration, so the first step is to dilate with a kernel. And then you compute the AND. These are sets, so the AND is also well defined. The AND is like the intersection. So you find which are the pixels that are in J and in I. So this is the intersection between I and J. And then you compare this new iteration. So this new iteration has included dilation and an intersection. And you compare it with your previous results. If it is the same, then you stop. If it is not the same, so the image keeps changing, then you iterate again. So you dilate and complete the intersection. And then you dilate and complete the intersection until it stabilizes. And here we have the result. So if you apply that, so you start with the opening. So you start with the opening. Sorry, I'm going in the wrong direction. So you start with the opening, and now you dilate the opening and complete the intersection with the original. And it has changed, so now you dilate again and complete the intersection. Dilate and complete the intersection. And now you recover the eyes. Now, another way to use this is to compute the skeletons. So in a skeleton, let's see the result. So let's say that you have a binary image like this, and you want to compute something that more or less tells you what is the kind, how to say, kind of widening of that. What is the minimal set of pixels that gives me the shape of that object? And let's look for some other skeletons. With a T, it is not so nice. But for instance, with skeleton binary. So you see, you have a hand. What is the minimum shape, minimum amount of pixels that give me what is the shape that I'm looking at? So for instance, for this one, it is this one. You may already recognize this one. What is this? You have already seen some of the papers. Okay. The veins of the eye fundus. Those are veins. This is the optic nerve. We recognize that. So what we want is to keep, for instance, if you have this image here, and you want to keep what is the minimum amount of pixels that give me the shape that I'm looking at. For instance, for the recognition of characters, it is very useful. So for handwriting, it's very useful to recognize what is the skeleton. Okay, so can I use these morphological operators to compute the skeleton? Okay, so the skeleton will be S, a set S. Those are the pixels that belong to the skeleton. And for computing this final skeleton, I will define the skeleton of a given size R. So I will have disks of radius R in I. And this radius, it is very interesting because, for instance, here we will see that the disks, they have a square shape. And I would like to expand your point of view of what a disk is. Okay, so let's come to here. So what is a disk? So you have, for instance, here the XY plane. You have a point that has coordinates x0. So you have coordinates x0, y0. And this is the disk of radius R. So why that is the disk? Because all these points here, so the disk is the set of points such that what? Such that the distance from, let's call it this R, from R to R0 is smaller or equal to R. Do you agree? This is the definition of the disk. And then, what is the distance between 2 points? So the distance between 2 points is the norm. It is the same, but it is the norm of that vector, the difference between the two. And this is square root of x minus x0 squared y minus y0. And then if I look all the points that fulfill this condition, all the points that fulfill this condition is a disk, it's a shape. Okay, so but there is an important observation here. It depends on your definition of distance. This definition of distance, this one, is the Euclidean distance. But it is not the only one. Okay, so for instance, I could define my distance in this way. I could define my distance. Yeah, let me rewrite this in this way. So this is x minus x0 squared plus y minus y0 squared. And then this is the square root. Okay, that is fine. Why not defining it in this way? X minus x0. This one, so if I give p value 3, then I have another distance. If I give p value 4, even 3.5 or 2.5 or whatever number I like, this is another distance. And this one is called the NP distance. This is the NP distance. And the Euclidean distance is a particular case. It is a L2 distance. But there are more distances. For instance, I can have the L1 distance. L1 distance is this one. Sorry. This is my L1 distance. And then what is the shape of a disk if I use the L1 distance? So a disk now looks like this. So I have my point here, and all these points are at a distance r. So the shape of your disk depends on what is your definition of distance. And there is another one. What if I make P I have L0 distance. So L0 distance I make P goes to 0. Or what if I make P go to infinity? What if I make P So, yeah, this one is the number of elements different from 0 from this vector. So, number of elements different from 0. This one is the maximum overall coordinates of r minus r0. this one, the shape of the disc is square. So this is very interesting, and we have seen this process a few times. But if you have some concept, relatively standard concept, but this standard concept, you may evolve it and generalize it quite a lot. Yeah, so the definition of the disk can depend or depends on what is your definition of distance. Okay, so now we have square disks because we are using the infinite distance. Okay, so let's go back to the definition. So the skeleton will be the union of many skeletons, but now these skeleton operators, they have a particular argument r. So what is the radius? And a skeleton of a radius r is the center of all maximal disks of radius r in I. So let's see it with an example. Okay, so let's say that I have this is the center of a disk of radius 1. This is the center of a disk of radius 2. This is a center of a disk of radius 1. Okay, good. Now, are they maximal disks? No, they are not, because I have a radius 1 here, but I can find another center of a disk of radius 2 that contains this one. So this is not maximum. Okay, so I can find another pixel that is the center of a disk of radius 2, and it contains this one of radius 1. So this one of radius 1 is not a maximal disk. And this radius 2 disk, is it maximal? Can I find another disk of radius 3 that contains this one of radius 2? I cannot, because if I construct a disk of radius 3, I go out of my object. Okay, and the same happens everywhere. So I have explained with this one, but for all the others, if you try to find a bigger disk, you go out of the object. So these red disks, they are maximal. The blue ones, they are not maximal. And if I now find all the locations of the maximum disks, so those are these red pixels. So this is a disk of radius 0. This is a disk of radius 0. This is a disk of radius 1. This is a disk of radius 1. This is a disk of radius 2, and so on. So my skeleton will be formed by all the skeletons of radius 0, union with the skeleton of radius 1, union with the skeleton of radius 2, union with the skeleton of radius 3, and so on. Okay, so this is my raw skeleton. So this is the skeleton computed according to this definition. And there is something inconvenient with these skeletons, that it is that there are disconnected pixels. So there are pixels that are isolated. So let's try to get rid of those. And there are holes too. So there are some disconnected components. Now we know what a connected component is. So that it is made of disconnected components. So let's try to have a single connected component and get rid of the small things. Okay, so yeah, this is the explanation of what we have before, the maximal disk and so on. These are all examples. Okay, so now how do we will prune this process of keeping the connected component, a single connected component, is called pruning and connection. Okay, so let's compute the skeleton first. So how do I compute the skeleton? So let's say I have this original image. I can apply multiple erosions. I erode 0 times. So 0 times those are for the disk of radius 0, right? Then you erode 1 time. And you have to define what is your extraction element. So I will use Z8 as extraction element. So I erode 1 time, 2 times, 3 times. If I erode once more, I run out of the image. I don't have any image anymore. So maximum disk is radius 3. And then you compute the opening with, what is this? Sorry. Yeah, you compute the opening of these erosions with a kernel with this kernel, set select. Okay, so this is the opening of this one, this is the opening of this one, this is the opening of this one, this is the opening of this, the opening of this, and so on. Okay, now I compute the erosion minus the opening. I compute the erosion minus the opening. And this is what remains. This is erosion minus the opening. And this is what remains. The same here, the same here. And now you take all these. So what we have down here are these skeletons of radius 0, radius 1, radius 2, radius 3. So those are already these images. And now you compute the union of all those. So you compute the union of all these, you have this one. And now with the colors, we know from which radius they are coming from. So these are radius 0, this is radius, the green is radius 1, radius 2, radius 3. So now I have the skeleton. Okay, so now we have the skeleton, we know how to compute it. Now let's prune it. So pruning is you compute connected components, and all those connected components that has less than 3 pixels, and this 3 is a number you choose. So all those connected components that have less than 3 pixels, you delete. So these ones, I didn't get rid of those. Okay, so those are the ones that remain. But they are not connected, so let's try to connect them. So what you can do is you dilate your skeleton and compute the intersection between the dilated connected components. So you have to do this for all connected components. So you compute dilation of this one, dilation of this one, and this one, but they are separated in 2 images just for convenience. And then you compute the intersection of all the dilated components. And you have a few pixels that appear in these intersections. This one that are halfway between full red and white. So these ones here, these are in these intersections. So the ones that appear at the intersections are the pixels you need to make all these components connected, and you add them. So you add those pixels, and now you have a connected skeleton. And you can imagine that this process of computing how to connect, how to compute the skeleton, and so on, you can be very creative there. So we have seen just one possibility, but you can create your own way of computing skeletons. And there are active research lines that area. I had to do this very efficiently and so on. So now we can compute this kind of things. So given an image, we can compute what is the minimum set of pixels that describe the shape there. A question? Okay, so otherwise we move to the next. Okay, so let's now extend these concepts of mathematical morphology. We have applied them to binary images. Let's extend them to grayscale images. Okay, so yeah, now we have to extend the concept. Yeah. So we will have one more dimension. So this is how we are used to think of a set. So let's say that we have two sets A and B, and I want to see, for instance, if A is included in B. So this A in red is totally included in B. This A is not totally included in B because it shares some pixels, but not all of them. Okay, so we are used to think in sets by thinking only of the location of the pixels. But now we will add an extra dimension, that is the grayscale. So now our sets, instead of being just a set of locations, is a set of locations that are in the XY plane, plus some height that is describing the gray value. And we will get more into the details there. But now the interesting thing is that make the color here. So we were used to think of sets in the XY plane. So our set was something there, that is the location of pixels in the foreground, for instance, with respect to the background. But now we will add an extra dimension, that is intensity. And now our set will have a shape. So it will be a three-dimensional set. And we will have to define all the operations, or at least a few of the operations that we are normally using in sets. We will do that. Okay, so yeah, we will use, you remember that before we said, we don't care what the values are, if they are 0 and 1, 0 to 55, they can be whatever. And here it is more or less the same. And when you want to refer to the background, we will use minus infinity or infinity. So instead of just the intensity being a real number, because we want to use infinity, we will use the extended real numbers. So we will include infinity as a real number. It is not. Infinity is a concept, it is not a number. But we will use R star, that is the one that includes minus infinity and infinity as numbers. And then you have to define your operations with infinity. So the addition with infinity is always infinity, subtraction from infinity is always minus infinity. And there is an ambiguity, that is infinity minus infinity, you don't know how to deal with it. But we will define it to be 0. Okay? So this is just a convention convenient for images. It has nothing to do with real mathematics. Okay, good. So now our images will be, you know, an image is a collection of pixels, and the pixels are defined by two things: the location of the pixel and the intensity at that location. So what is that? We will consider only grayscale images, not color images for the moment. So for grayscale images, so P has two dimensions. The intensity is an extra dimension, so this will be a three-dimensional set. Okay, good. So what is the support? So the support of an image, now this is not binary anymore. So the support of an image is the location such that the intensity has a real value. So now we have the possibility to take infinity or minus infinity. So all these pixels here, so for instance in the background, the pixels in the background will be set to minus infinity. Okay, so just to say they are in the background. And we have the same concepts as before. So once you define the set, like the support, you can define the complement of the support. Okay, so now our sets will look more like this. So let's say that we have a gray scale image like this one. So we can, so let's say that this has values 1, so 0 outside, 1, or minus infinity outside if you want. 1, 2, 3, 4, 5. So you could have this shape. So this shape, this U here is this U. And then you have the values 1, 2, 3, 4, 5. Okay? And so our sets will be these shapes. And here you have another example. So now we have this image, and we have these gray values, and now this is the set that represents this grayscale image. And we have to define the inclusion. So for the standard sets, these ones here, it is clear what the inclusion means. So inclusion means the support of J is totally included in the support of I. So here the support of J is totally included in the support of I. So that is why you say that J is included in I. And here the support of J is not totally included in the support of I. But now with these three-dimensional sets, how do we define inclusion? So we define inclusion in this way. So the support of J has to be totally included in the support of I. And now, so this is in two dimensions, but now in the third dimension, we have to also define inclusion. So we say that J is included in I if for every pixel in the support of J, the gray value of J is smaller or equal to the gray value of I. So let's see a couple of examples. So for instance, this is J, this is I. The support of J is included in the support of I. And the gray value of J is always smaller than the gray value of I. Here, the support of J is not totally included in the support of I, so J is not included in I. What about this one? Here it is the same. The support of J is not totally included in the support of I, so they are not included. Here they are included, so the support of J is included in the support of I, but the gray value of J is larger than the gray value of I. So J is not included in I. So to be included, to an image to be included in another image, it has to be that the two supports, so the support of one is inside the support of the other. And the gray values of one are always smaller than the gray values of the other. Any question?